Hi, my name is Nick Kuuttila, and I'm going to be talking about 2D heat conduction in the hydroforming manufacturing process. Thermohydroforming is an MSU patented composite forming process that uses a heated pressurized fluid. This fluid itself can reach temperatures up to 600 degrees, but the seals that hold in this fluid cannot reach temperatures above 300 degrees or they begin to degrade. Heat from the hot oil is conducted through the die and can heat the seal seat to elevated temperatures. The simulation was performed to see how long until the seal seats reach a critical temperature where the seals will begin to degrade. The dies are steel cavities that have constant temperature fluids circulating through the upper and lower zone. The side zone is isolated from the circulating fluid, therefore it has a lower convection coefficient and an ambient temperature that shifts with each time step. First, the domain is clipped to include regions that both have heat added by the oil and heat removed by the air. The geometry is then fed into Abacus CAE where the domain is discretized. The mesh includes about 2,400 nodes and 1,100 elements. M and K were constructed in MATLAB using local coordinate triangles. M itself is a function of the shape functions, while K is a function of the shape functions, the thermal conductivity, and the elemental geometry.
The forcing functions of the simulation all come from convective boundary conditions. The addition to the global stiffness matrix is a 3x3 matrix, which is a function of the convection coefficient and the boundary length. The addition to the global nodal loads is a 3x1 matrix, which is a function of the convection coefficient, boundary length, and ambient temperature.
Accurate convection coefficients are key if you want to obtain a good result. Nessel number correlations were used in order to characterize the fluid flow at each boundary in order to estimate the convection coefficient. An explicit time marching scheme was used instead of the ODE23 function in MATLAB due to its simplicity. It was found to be stable as long as the chosen delta t was small enough. The explicit scheme also allows the ambient temperature and therefore the nodal loads in the side zone to be recalculated at each time step. The shifting ambient temperature in the side zone is really the pride and joy of this project for me. By knowing the volume of the fluid contained in the side zone, we can calculate the heat leaving the fluid at each time step. Using the heat capacity of the fluid, we can then find the change in temperature and use that to calculate the T ambient for the next time step. Once the simulation was completed, temperature contour plots were output at 5-minute intervals all the way up to 30 minutes. We see heat entering primarily through the upper and lower zones, convecting out towards the exterior. The max temperature at 30 minutes was 162 degrees. When examining the seal seats, we see that the steady increase in temperature occurs all the way through the simulation. This shows us that the temperature will increase much more, but it will take well over an hour to reach a temperature where the seal degradation is a real threat. The results from the ambient temperature boundary condition are also what we would expect. The fluid temperature is decreasing throughout the simulation as it gives up its heat to the die boundary, which we see is increasing in temperature. A steady-state solution was also performed and predicted that the entire die will eventually reach temperatures well above 300 degrees. This, however, would take a matter of hours, and the forming process itself takes about 10 minutes. In conclusion, the temperature seems to increase at a very slow rate. As dies are exceptionally large and have the capacity to absorb a lot of heat, so we have to keep that in mind. The temperature difference between the interior and the exterior is also much smaller than expected, so perhaps a good way to estimate the temperature of the seal seat is simply by measuring the temperature of the exterior. So now I'll be willing to answer any questions you may have. Thanks for listening.